There are 200 people at the beach, and 65% of these people are children. If 40% of the children are swimming, how many children are swimming? 200 is the initial, and of those, 65% are children. So 65% of 200 is 130. Now, of those 130 people that are children, 40% of those are swimming. So 40% of 130, I believe, is 52. And that's it. X plus 2y is 14. Y is 3. What is the value of 2x plus 3y? So first, let's plug that into there. So x plus 2y, well, y is 3, so that's 14. So x looks to me like 14 minus 6, which is 8. And then now we subbed in those values. So 2 times x, but x is 8, and 3 times y, and y is 3. So that's 16 plus 9, and that is 25. In the diagram, ABCD is a rectangle, and points P and Q are on AD, so that AB is equal to AP is equal to PQ is equal to QD. Also, point R is on DC with DR equal to RC. If BC is 24, what is the area of triangle PQR? So let's label this. So BC is 24, right? So these three are equal, so that's going to be 8, 8, and 8. And then did they give me the value of anything else? I think that's it. Oh, but they give me the symbol. I got it. You see the symbol right here is also there, so that means those are equal, so that's 8. So therefore, these two guys, DR and RC on the other side, are 4 and 4. Okay, so the area of triangle PQR would be 1/2 base times height. So what's the base? The base is from there to there, which is 8. And the height would be from here to here, which is 4. And therefore, that looks to me like 16. At a given time, the depth of snow in Kingston is 12.1 centimeters, and the depth of snow in Hamilton is 18.6 centimeters. Over the next 13 hours, it snows at a constant rate of 2.6 centimeters per hour in Kingston, and a constant rate of X centimeters per hour in Hamilton. At the end of these 13 hours, the depth of snow in Kingston is the same as the depth of snow in Hamilton. What is the value of X? Kingston, which is where Queen's University is, and Hamilton, where McMaster University is. I've been to both, and they're saying that 12.1 and 18.6 is the snow. Now, that is the depth, right? Now, they also give us a rate that's 2.6 per hour, and there's 13 hours of snow. And in Hamilton, they don't give us the rate. They just say it's X centimeters per hour, and then that's also going to be for 13 hours. And then they're saying that when this 13 hours is completed, the totals are equal. So that basically means that 12.1 plus that 2.6 times 13 is equal to that 18.6 plus that 13x, like that. So this is 45.9, and that's 18.6 plus 13x, and therefore this would be 27.3 is 13x, and when you solve for x, you will get 2.1. Scott stacks golf balls to make a pyramid. The first layer or base of the pyramid is a square of golf balls and rests on a flat surface. Each golf ball above the first layer rests in a pocket formed by 4 golf balls in the layer below. Each layer, including the first layer, is completely filled. For example, golf balls can be stacked into a pyramid with 3 levels, as shown in Figure 2. The 4 triangular faces of the pyramid in Figure 2 include a total of exactly 13 different golf balls. Scott makes a pyramid in which the 4 triangular faces include a total of exactly 145 different golf balls. How many layers does this pyramid have? So I'll keep the photos. we're going to have to make a little bit of a table, and we have to do an extrapolation because obviously I'm not going to draw it out. It would be way too messy. So layer 1, layer 2, layer 3, layer 4, and so on. Like I'll just go up to 5. Now, if you look at these figures, the first layer is just one, what is it, balls? Golf balls, I think, yeah. And then the second layer is 4. And then the third layer looks to me like 9. So those are perfect squares. I think most people can figure that out. 1 squared, 2 squared, and 3 squared. So that means this one will be 4 squared, which is 16. This one, next one will be 5 squared, which is 25. So you can figure that out pretty quickly. You certainly do not have to draw them out. You can if you want, if you have good 3D drawing skills, but I don't think it's necessary. Now, the next column or whatever, cumulative total, that is something we really need to talk about. And then finally, the triangular faces, that is something we need to talk about. Triangle faces, let's just write it like that. Okay, so the cumulative total is referring to what is the total of the entire figure. So in figure 1, you can just see the entire was 1 at the top and then 4 on the bottom. So that's a total of 5, right? Yeah. So the 2 layers, when you had 2 layers. And if it's just 1 layer, then of course that's just 1 golf ball. If it's 3 layers, which is what figure 2 is, then it would be 9 plus 4 plus 1, correct? And that's 14, I believe. And then similarly, you just add them up. This is going to be 30, and that's going to be 55. Now, the question, if you go back to the question, they, unfortunately for us, are not talking about cumulative total. What they're talking about is the triangular faces. So I guess this should have been triangular faces. And that is not cumulative total, interestingly. It's tempting to think that it is, but it's not. Let's talk about it. So let's just look at this one here, that figure. This is a triangular face, right? And that triangular face, you can count, has 1, 2, 3, 4, 5, 6. 6 golf balls. Now, what would be the total of the 4 triangular faces, right? The 4 triangular faces. Well, it's tempting to say 6 times 4, which is 24, but that's wrong, because then you double count. See, in this triangular face, you've already counted these 3 guys. So you only have to count this one, and this one. So you'd count another 3. And similarly, the face that's there that we can't see would have another 3. So you'd have 6 from the face that's facing us. Then you have 3 from this side. And then you have another 3 from that side. And then from the one on the back, you'd have only 1 additional one. And that's because it would be this one, but on the other side. So that total of 6 plus 3 plus 1 is 13. So that is what would go here. And they've even told you that. They've told you that it's exactly 13. So they helped you out a little bit. Okay, so these 2 guys, we don't care. Now, I want you to do this one and this one. It takes a little bit of thinking, but I think you should be able to. And when you do, you get 25 and 41 as just the number of golf balls in the 4 triangular faces of those all those layers. Okay, so now we have to start extrapolating because we want to eventually get how many layers are there. So this number, whatever this is, when this number is 145. So how many layers do we get a triangular faces total of exactly 145 golf balls? So to show you how to get that, I'll probably need to draw a little bit of a diagram. So bear my non-artistic skills, but I'm going to attempt to draw. I think 5 layers should be enough, and that should be enough. Okay. So how do we come up with this? let's just say that this is 5 layers, right? Which it is. First, you look at one face, and if you count all these guys up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 15. And then you would count the triangular face on the opposite side, and that would actually be 14. Why? Because this guy at the top has already been counted. That guy. So, but all the other ones will be different. So that will be the back one, the back triangular face. This is the front triangular face. Now the sides. The sides would only count these ones. What I mean is the ones that are in that particular location. Because all the other ones have already been counted. So that's 6. So the sides, there's 2 of them, 6 and 6. Okay, that's great. But I am not interested really so much in that these numbers. I want a general kind of rule. Because a general rule is what I'm going to use. Okay, not a problem. This is basically the sum from 1 plus 2 all the way up until the number of layers, which in this case was 5. This is the same thing, but you then subtract 1 because you already counted that top guy. Now these guys are the same thing, but you're only going up to the third layer. You see what I mean? So if this was 5, you're only going to 3. And similarly, 1 plus 2 plus 3. So I think I can extrapolate that for any layer. So this is for layer 5, right? So if my layers, let's say, are just n, meaning I don't know what it is, that's okay. The front one would be 1 plus 2 plus 3 all the way up until n. This back one would be 1 plus 2 plus 3 all the way up until n, and then minus this one, right? And then this one, let me think about this for a second. 1 plus 2, okay, I think I got it. 1 plus 2 dot 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 all the way until n minus 2. Because this was n, and we're going 2 less. I'm pretty sure that's the way to do it. And then similarly, this would be the same thing. Okay, so now let's do the math here. This guy, you guys know that formula. It's n plus 1. It's n times n plus 1 over 2. This one is the same thing, n times n plus 1 over 2, but then we got to subtract that 1. And then this one would be, we're going up to n minus 2. So it would be n minus 2 times n minus 2 plus 1 all over 2. And then there's 2 of them, so we'll just stick a 2 out front. We'll just times that by 2. I'm pretty sure that is correct. All right, so let's do the math here. Now we got to do this algebra. And all of this has to add up to 145, right? Yeah. All right, let's see what happens. Hopefully this is right. So, well, these two guys combine, so that just becomes n times n plus 1. And then we got this minus 1. And then this one just becomes n minus 2 times n minus 1. Yeah. Okay, let's expand this now. 145 n squared plus n minus 1 plus n squared minus n minus 2n plus 1. So 145 would be 2n squared. That cancels minus 2n. And, oh, sorry about that. This is 2. Good thing I caught that. So this is plus 1. Okay. All right, let's continue with this algebra here. Put everything on one side, and we get 2n squared minus 2n minus 144. I think we can divide out a 2, n squared minus n minus 72. And I think this factors very nicely. n, 8, and 9, and then plus and minus. So there you go. N would be 9. That's the only positive solution, and therefore we can conclude that the number of layers need to be 9. A positive integer is a prime if it is greater than 1 and has no positive divisors other than 1 in itself. The integer 43797 has the following conditions. Each pair of neighboring digits forms a 2-digit prime number, and all of the prime numbers formed by these pairs are different, because 43, 37, 79, and 97 are all different prime numbers. There are many integers with more than 5 digits that satisfy both of these conditions. What is the largest positive integer that satisfies both of these conditions? So we want a number that we have, I don't know how many digits it's going to have, but ... And then whatever numbers you put in here are going to be prime. So for example, we had 43, and then they had 37, then 79, then 97, and then you could put in, say, 71, and then 13, and so on, right? And then just keep going. So they're saying, what's the largest? Okay, so there's a multi-step process here. So the first thing I'm going to do is, since we only care about 2-digit prime numbers, I'm going to write out the 2-digit prime numbers, and then we'll talk about them. So we got 11, 13, 31, 37, 41, 43, 47, 53, 59, 61, 67, 71, 73, 79, 83, 89, and finally 97, I believe. Okay. So there's 21 of these guys, and, well, are they? I think 21. Yeah. So let me write that down because that's an important point. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Yeah. So 21 prime numbers that are 2-digit, and they all end in either 1, 3, 7, or 9. So all end in, I believe, yeah. So none of them end in anything else. Okay, so that's one thing to consider. Okay. Now let's talk about the number, right? What's interesting is that some of these numbers will never be usable. Yeah, some of them will never be usable. And the reason is, I'll explain why. It's kind of an interesting reason. You notice how you start off with some prime number, right? In this case, it was 43. And then you take this number to start the next prime number, which we put, well, they actually put 37. Then you take this number to start the next prime number, and so on. So whatever number you're using, let's say we have a 3 here, you use that number to start the next prime number. So is there any prime number that begins with 3? And the answer is yeah, there's a couple, so I can put 31 in here. So that makes me think that, with the exception of the first one, which seems to be the only exception, every other number has to be one of these guys. Is that the right assumption? Yeah, because that's the only way you could start another number. For example, if the number here was 4, right? You can say, okay, I can make a prime. I can put 47. But there's no way for you to have made that 4 because 14 is not a prime number. You see what I mean? So what that does is it eliminates this list of 21 down to a much smaller list that consists of prime numbers that only begin with 1, 3, 7, or 9. So it's 11, 13, 17, 19. You skip the ones that begin with 2, 31, 37. Skip the ones that begin with 4 or 5 or 6. And then 71, 73, 79. And then you skip the ones that begin with 8 and then 97. So this is what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we now have only 10 prime numbers to work with. Okay, so that's the first sort of step for this kind of multi-step question. Okay. So now we go back and say, okay, if I'm going to make this prime number, I have no idea how many digits. But one thing is for sure is that first prime number is an exception. So that could come from that list. All right? But all the other ones, like this one and this one and this one and so on, those all have to come from this list of 10. And that's just the way it is. So let's say we used all of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And let's see how long it would be. How long would the number be if all of them were used? Because we're trying to get the maximum, right? So it'd be one number. Remember, the first one is an exception. This would be the first from that list of 10. Second, third, 4th, 5th, 6th, 7th, 8th, 9th, and 10th. So we'd go to here. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12. So 12 is the maximum digits that this prime number could have based on our findings so far. Okay, so I guess we don't need this guy here. All right, so now we get to the next step here. Now we got to start talking about how to make this prime number, where the first number could come from this list, but then the next, however there are, I actually don't know how many there are, but if I try to make it maximum, they would all come from this list here. Okay, so then how do we decide now which number to use? Okay. I guess we have to match them. So just concentrating on this list right here for now, this list right here, we have to sort of match them. So how many of those begin with 1? 4 begin with 1, right? 4 begin with 1. So these guys, 1, 2, 3, 4. And then 2 begin with a 3. 2 begin with a 7. No, sorry, 3 begin with a 7. And then only 1 begins with a 9. Now, the reason I did that is because I have to match them, right? Because if something begins with a 1, it had to maybe be preceded by something that ended in a 1. You see what I'm saying? Like, for example, if I put like 1 here, let's say this was 13, then this had to have been like a 71. So if some number began with a 1, the number before it had to end in a 1. So that's why I got to figure out how many begin and how many end. Now look at the endings. 3 end in 1 from this list right here. Right? 3 end in 1? Yeah, the 11, the 31, and the 71. And then 2 end in 3. 3 end in 7. And 2 end in 9. Okay. So that helps. I think that helps because now I can figure out how to place these numbers. So let's make an attempt here. I'm not sure. So I got 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? Because I'm trying to make the max. Okay, let's talk about the first one. 4 begin with 1 and 3 end in 1. So that means that 3 end in 1. So let's just say there was a 1 here, a 1 here, and 1 here. I don't know. I'm just kind of playing around here. But 4 begin with 1. So that means that 1 has to go there. You see what I mean? Because this one doesn't have anything to match with. Yeah. Yeah, that doesn't have anything to match with, so I'm pretty confident that will go there. These match perfectly. 2 begin with 3, and 2 end in 3. These also match perfectly. 3 begin with 7, and 3 end in 7. This one is a mismatch, though. 1 begins with 9, and 2 end in 9. So that means there's 1 extra ending. So since there's 1 extra ending, that's got to go there. So this helps me figure out this position and this position. Okay, so we made a little bit more progress there. Now the next step, I'm going to try to figure out 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I got that as a 9, I got that as a 1. My next step is to figure that out. That is going to, remember, that's the exception. That's the one that comes from this list here. Okay, so what is it again? It's a number that ends in 1. So I now I'm trying to make the largest, right? The question asks to make the largest. So let's look at this list and see what's the largest one that ends in 1. It looks to me like 71. 61. Well, 71 is the largest. So let's try 71. Let's see what happens. If I put 71. Oh, okay. I'm not allowed to use 71 because 71 is in this list. I have to use something that's in that list, but not in this list. Ah. Yeah, because all of these guys, these 10 have to be put into the other spaces. So the largest number that's in this list that ends in 1 that is not in this list, the second list, is 61. Okay, so that makes 61. Okay, so I think I'm ready to fill this out. So let's do it. I think the rest we can do it. So we're going to use these guys up here, these 10. And let's see what we can do. I'm concentrating on the largest. Okay, so we got 61. So now this 1, we want to make this number as large as possible. So of the numbers up here, the largest number that begins with 1 is 19. So that will go here. So 19 is taken care of. Now we have a number that begins with 9. The only number in here that begins with 9 is 97. Then we have 7, so we have to choose a number that begins with 7, concentrating on the largest one. So the largest one is 79, but I don't want to put 79 there because the 79 has to probably go, the 9 has to go here. So I'm pretty confident that the 79 goes here because that's the only way this number would work. But the next number I'm going to put here, 73. So it takes a little bit of thinking. Same kind of story. 3, the largest number would be 37. 7, 71. That's pretty straightforward. Then 1, the largest would be 17. But I'm pretty sure the 17 has to go there to make that work. So then that means the 13 goes here. And then the 31 goes here. And then the 11 is there. There you go. 6, 1, 9, 7, 3, 7, 1, 3, 1, 1, 7, 9. So it's a very challenging question, I think. But if you go through the steps and kind of work through it, you should be able to come up with the right answer.